This is a very long derivation. We have the 3 weeks derivation. Okay, understand? Do you remember what we did for 2 weeks ago? We start from the general solution of an electric field. Okay, this is about the derivation. First of all, let me make a quick review to bring you back. Maybe you forget. In case you forget. So we start from this part. This is what we discussed 2 weeks ago about the general plane wave solution. What does that mean, general? General means, comparing to what we discussed in chapter 1. In chapter 1, we discussed only about the TEM mode. If you have electric field, then you have a magnetic field perpendicular to your electric field, and also your wave is propagating in the third propagating direction, which is a P, when we discuss about a pointing vector, okay, X, Y, Z. So these 3 directions of vectors are perpendicular to each other. This is what we discussed in chapter 1. But now we have something different in chapter 3. In this case, we try to introduce you something different, which is waveguide. So in waveguide, your E field has not only the direction of X and Y, but also maybe something exists to the direction you propagating, the Z direction. Okay, and also for your H field, you have not only Hx and Hy, you have also maybe Hz, maybe. I didn't say that always exists. I didn't say never exists. Sometimes it exists. Okay, in some different mode. The mode we discussed, which is not just TEM mode. We have also TE mode and TM mode. Okay? Okay, this is what we discussed. And we start from the best concept, the definition about the general plane waves. We have 2 assumptions. First of all, the wave is lossless, so we use beta instead of gamma. We try to simplify the equation from a lossy case to a lossless case. We use beta instead of alpha plus J beta, right? Actually, we use J beta. We discuss only the lossless case. Okay, this is the first assumption. The second is we always use, we try to insist our directions to just only Z direction. But in chapter 1, we have different waves. We have the forwarding wave and the reverse wave. But in this case, we try to simplify the question to only the forwarding wave. So the wave is propagating to only positive Z direction. Okay, those are the 2 assumptions we made at the beginning 2 weeks ago. Want to come back here? It's fine. It's just that's fine. So I just make a quick conclusion about what we discussed 2 weeks ago. So here in this page, this is a quick conclusion for 2 weeks ago about the general lossless, the E field, or actually not only E field, and also H field E and H propagating along the positive direction, positive Z direction, and we separate EZ and HZ. We use different notation to regard this as new notations, okay, new unknowns. We try to treat this spatially. This is what we discussed 2 weeks ago. Okay, what did we discuss last week? According to this assumption, we try to, if there is a sourceless, if this is a sourceless case, which means in Maxwell's equations, you don't have capital M and the capital J, these two source vectors. If you don't have source, you can directly use the Maxwell equation, the first and the second equations, and put all of our general E field and H field inside directly. And what we need to do is just you use the technique of the curl. You put the EX, EY, and the EZ inside for the left part, and then you put HXYZ for the right part. We just directly do that. For each equation, for the Maxwell equation number 1, because you have X, Y, Z, so you will obtain 3 equations from the equation number 1. Okay? Then you also can obtain 3 other equations for equation number 2. So therefore, you will have 6 equations. Okay, so this is a question, this is from these 3 equations came from question number 1, because you have X, Y, Z, right? Then, because you know, according to our assumption, your partial differential with respect to Z can directly become minus J beta. You change this part to minus J beta, then your equation number 1 can result in 3 new equations for the Maxwell equation number 1. Okay. Also, you can obtain another 3 equations. This is from Maxwell equation number 2. So you have 6 equations. Okay. By using these 6 equations, you can find out there are, think about that, you have 6 unknowns and the 6 equations, right? We try to solve that. We try to find out some rule. For example, for this equation and this equation, you can cancel EY by these 2 equations, and you can obtain. You can cancel EY. You can eliminate the EY. Then you can obtain the equation HX, and it will be the answer of something relevant to EZ and HZ. Okay? And last week, because we see this spatial denominator, we defined this red box. We define that to a cutoff wave number. We define this red box to the square of the cutoff wave number, KC square. We define another notation Because we know if this is 0, something happen, and if this is not 0, something happen. Okay? There are different cases. It depends on if that red box is 0 or not. So that is a cutoff, something like age. The age, what happened at when this one, the red box is 0. So this one is KC square. And you can try to carefully see that the blue box here, it is the wave number we discussed before. Because the notation, the unknowns, they are totally the same. It is omega squared multiplied mu epsilon. This is what we did at the very beginning. We make an unknown. We try to define this as a k squared, okay? And this is also the beta, okay? It's a propagation constant or phase constant. Okay, this is how the wave propagate, the beta, our old friend, which is very important, okay? So we obtain this one, it is KC squared. All right, so we obtain one of the solution, Hx. This is what I wrote down here. Okay, which one we are trying to obtain? Which one is the most important? What is the final result we want? The final result is we want to know what is total E. What is the E field, right? This is what we want. And also, what is the magnetic field? This is what we want. And the E field, it has the X component, Y component, and also the Z component. And according to what we derive here, we can understand that once we obtain Hz and Ez, we can recover everything. We can recover everything by after we know Ez and Hz. Okay, this is what we are going to do today. And how to find Ez and Hz? By using the definition when we use for the TEM mode, because in the TEM mode, K equals to beta, okay? And only if K equals to beta, we can make the denominator for this term, the denominator equals to 0, and we can still get the E and the H field. So we know K must equal to beta. Once K equals to beta, we put them inside this equation, then we can obtain this relationship. This is one of the things, this is just only one of the equation we can treat to not only Ex but also Ey, Hy, Hx and Hy for the TEM mode. Okay, but this is not the most important thing we try to explain here. We use very similar technique for TE mode. For TE mode, we know Ez equals to 0, but we have Hz. So we don't have this term. We have only this part for TE mode. For TE mode, we have only this part because we don't have this term. Okay? And by using very similar calculation, you can obtain this equation. Because you put kc squared equals to k squared minus beta squared in here, right? You put here, this is not, they are not zero together. When they put them together, they are not zero. They become kc squared, right, for the TE mode here. So you will obtain this equation. Okay. I will try to write down this equation here. Okay, just try to remember this equation. This is the equation for TE mode, right? And I put the same equation, and you can still see the equation here, right? The capital 1 equals to the small 1 multiply the exponential. So you can have the same equation here. This is where we start for today. Please turn on the light, please. What is our goal? Our goal is we use the equation we derived last week. We start from here to find out what is the red one. What is this one? Okay, we use this equation to find out what is Hz. And okay, maybe I can write down here. So Hz, this one, equals to small hz multiply exponential minus beta z. Okay? This is the difference between the capital and the small letter. Because for this one, you don't have x and y, so we can just directly go to check what is the small hz. So this is z. Okay? Can we start from here? So I will try to solve this one. Then after I solve this one, then I know the capital Hz is your answer multiply the exponential term. Okay? After you have the capital Hz, then you can recover all your field. You guys need to take some time to understand. You guys don't follow. You can follow? You can follow? Okay? You guys follow or not? If not, maybe I can explain again. Okay? So we need to solve this equation. Okay. So what is the first step to solve this equation? First of all, we know it is a function of x and y. Okay? So the first step is we try to set h, x, y equals to, we try to separate the unknown. Is that okay? If it is separatable, we try to separate these equations to two parts. Okay? We try to make the assumption it is separatable. So h, x, y is a function of x, and the y can become part of the function x and a part of the function y. Okay? So what can we change this to? So this one become s and y. Okay? So the next step, we just try to do that. So just put everything here. So because you try to take the second derivative to x, so y will not change because this is a function of only y, right? So you want this one becomes 2 and x plus x y plus kc squared x y. Can you follow? I just put them there, but because this is differentiate to x, right? So you can put this term outside. Okay. Can we divide this term, the whole equation, to the capital X and the Y? Okay. Divided by capital X and Y. So this one can become 1 over x plus y plus kc squared. You divide x multiply y, the capital S and the capital Y. Okay, so this equation can become only this one because you cancel y, but you also have x. You cancel x, you also have y, and then you have the kc squared. Okay? What's next? Okay. So the next step is, you see that for this term, only x, everything is x, right? So for this term, that's only y, everything is y. And this is kc. Okay, so we try to separate it again. We set another set, kc squared equals to kx squared and ky squared. It is the cutoff wave number in x direction and the cutoff wave number in y direction. We separate that. We use another assumption. Okay, So, can change that. K x squared plus ky squared equals to 0. Okay? And then we try to separate x and y. So, plus k x squared equals to 0 and y for the first one is the x, take the second derivation, right? Plus, you multiply x to both of them, so it will be k x squared x equals to 0 and y. You multiply the capital X for whole equation, then you append this one, and this one actually this is I just used a different notation. This is the same, right? I'm just lazy because we sometimes use the double prime. We use the double prime, but this is the same. This is the same as this term. This one is the same. Okay? You, in the calculate class, maybe they use this notation for the second order derivation, right? Right? No? Did you guys took a calculus class before? No? You did it, right? Okay? So, what is this? Guys, something take the second order, take the PDE, the second order PDE plus something square, multiply something equals to 0. What is the answer? What's the answer? Okay, let me show you the answer. With equations, you take the second order of PDE plus k squared, multiply the same thing equals to 0. Remember these equations? This is chapter 1, right? And we know for these two equations, we will have an answer, the general answer. Okay, maybe you can, this one is more close to our case, because that one is a vector and this is scalar, right? You take the second order of z squared, right? Multiply something plus k squared and multiply your equation. What is your EX before? The answer is the form of some magnitude multiply exponential to minus jkz plus some new magnitude multiply exponential positive jkz. Remember? Wave equation. So let's compare 2 pages. We try to compare 2. The answer of wave equation here, and this is what we try to find out. Right? Similar, we should have for this equation, you have this answer. And how about this one? Okay, please help me to turn on the light. Okay, so we know K for this case S you will obtain your X equals to some magnitude. Maybe we call that, okay, call X0 plus. This is not the same in your test proposal or in my PowerPoint. I just use very similar, okay? Multiply exponential minus j k x x plus another magnitude and the positive kx x. Okay? And y equals to y some magnitude multiply exponential minus j k y. No, this is unknown. It's y plus y another magnitude y0 minus. Okay, you just change the notation. Okay, I use different. Yes, thank you. It's another magnitude. Sorry, typo. Exponential positive j k y y. Okay. Beautiful, huh? Beautiful. Coincident. Again, go back to our wave equations, right? So what are we doing? We are trying to solve small h to obtain a total E and H field, right? But the small h can separate into only x and the y component. And the x component can be written as this form, and the y component can be written like this form. Okay, understand what we are doing? Okay. Then we can use the Euler equations. You guys remember Euler? We'll try to do that. Exponential j theta equals to cosine theta plus j sine theta. Okay, we try to change our exponential form to cosine sine. So for the first one, okay, erase it, and you can go back to read, to watch video. that later. So x, to use the Euler, the equation of the Euler rule, we change your x of x, the capital X of small x, equals to the magnitude multiply cosine kxx, because minus cosine. Cosine minus theta equals to cosine theta. So I just neglect the negative sign here, okay? Minus j sine kxx. Okay? This is for this term. Plus x0 minus multiply cosine k x plus j sine k x x. Right? I'm right? Positive, 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 negative. For this one is this term. You guys follow? I see 3 of you are sleeping now. Okay. Just try to wake up. This is 3 weeks derivation. Okay. It's okay if you are sleepy, but if you can understand, it's not everyone can do that. Okay. So this one can equals to, let's organize it to only, we try to change that to only cosine and sine terms, right? We can do that. So this one equals to x0 plus x0 minus cosine kxx plus j minus x0 plus x0 minus sine kxx. I just put cosine together and put the sine together, okay? Okay? I call this, because this is a magnitude. This is another magnitude. We don't know it is, right? 2 unknown put together, we can call a new unknown, A, still an unknown. Okay? For this one, I can take J with these 2 terms together. I called all of them B. Okay, remember I put J inside. B equals to J multiply this term. Then something become more beautiful. Okay. So what we obtain? We obtain, let me write down. So x equals to A multiply cosine kxx plus B multiply sine kxx. Okay, this is our result. Because we don't know what is x0 and x0 plus and x0 minus, so when we put them together, we can give it a new name. It's fine. It is just a some magnitude we don't know, some magnitude we don't know. Okay, both of them are unknown. So when they put together, there's still something we don't know. Okay? Then you do the same thing for y. Y look very similar to x, right? So you can just directly set c k y y plus d sine k y y. X and y. Okay. If you are getting simple, it's okay, because now you are in the most difficult part of microwave engineering. This class, this week is the most difficult in whole semester. We spent 3 weeks to derive. And you know, microwave engineering is one of the difficult class. So this is the difficultest of the difficultest. So don't worry, but try it. Maybe you can do it, right? Maybe you still can follow. This is the most difficult of the most difficult. Okay. Try to follow me. Try to understand the logic in your textbook. I'm helping you to understand this difficult stuff. So your x and the y can be written as this part. And this is what is your x and y. X multiplied by y, it is your small h. And once you got a small h, you have capital H. Once you have capital H, you have everything, right? So x and y are important. Try to solve everything. Once you got the result of x and y, you know everything. Okay, this is how we derive. Okay, so don't need this anymore. Therefore, so your small h and y equals to your capital X multiplied capital Y equals to, let me just write everything. C cosine k y plus d cosine k y this is x y. And I don't need this. So your small one is this one. Okay. So let's go back to see the boundary condition. Please. everything is connected. That's why we need to introduce everything at the beginning, and then we will use them again and again. Maxwell equations, boundary condition, wave equations, right? Not only show up one time, you show up maybe 2 times, 3 times, again and again. Everything is important. For the boundary condition, let's go to the quick result. Okay? If there is a boundary, we know the first 2 equations is about the normal, the direction of D and the B. Okay. And for these 2 equations, is about the E field and H field for the tangential direction. Okay? Tangential equation for these 2 equations. If you have the E field and the H field, this direction and this direction, they put them together for equals to, if there is a source, but if there is no source, E field in this direction and E field in this direction, they are the same, right? Remember boundary condition? We explained that carefully at the beginning before your midterm. Okay. This is the 3rd boundary condition. Okay. Okay. Let me. Please. Thank you for help. This is our waveguide. I have you guys know waveguide, right? There's a rectangular waveguide. We have 4 metal walls. 4 metal walls. We have 4 boundaries. So we can apply boundary condition in boundary 1, 2, 3, 4. There are 4 boundaries. What are them? Air, metal, air, metal, air, metal, air, metal, right? We have metal for outside. We have air inside. For these 4 boundaries, we try to solve 4 boundary conditions. Okay, let's name these 4 boundaries. If I call this boundary number 1, okay, and I forgot, let me use the same boundary. Oh, no. This is boundary number 1 for this boundary, okay, and for this, I call this boundary number 2. And for this boundary number 3, and this is boundary number 4. Okay, let's take a break. We'll come back. Try to take a rest.